So we've just done this part here. They've drawn the 3 op-amp instrumentation amplifier, and we've written down the expression, including the circuit fragment. So the second part of the question here involves this circuit QB here. And if you look, it has some form of differential amplifier. It's got sense and ref and all that good stuff. This symbol here is just a connector symbol, so don't be confused by it. It just means that it's a coaxial connector, and the circle part is the outer braid of the cable, and the inside part is the pin, the center core. So we have here a differential amplifier, and we've got this sort of funny circuit at the beginning. So let's have a little read. And it explains that it's a test setup for phono cartridges, old-fashioned vinyl, and the equivalent model can be represented by a voltage source in series with a source resistance, which is 475 ohms, and a series inductance of 700 millihenries, driving a test resistance of 47 k ohms. Due to the test equipment, there is a common mode voltage between the cartridge ground here and the instrumentation amplifier here of 10 millivolts RMS. So we've got 2 different earth points here, which are nominally the same voltage, but there's actually a signal between the two due to a voltage happening at the input. Voltage across the 2 earths. It then goes on to talk about phono cartridges, and the phono output is Vt equals 2 times pi times F times A, where V is the velocity, F is frequency, A is the amplitude of the recorded groove on the vinyl record in meters. And it then says a standard test used by the industry is blah, 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 and a velocity of 5 centimeters per second. For a given cartridge manufacturer, the output voltage VC under these test conditions is 5 millivolts RMS. So that's given you a little bit of background. In most of my questions, I will always have some sort of application thing. Read the information carefully. It's not there to spook you. It's not there to confuse you. It's there to try and make you think about the application. So even though it's talking about meters per second and things like this, bear with it. It's not a big deal. It then says that the smallest detectable signal from the cartridge is 400 nanovolts RMS. If the signal at the instrumentation amplifier output, Vout, due to the common mode signal, now remember back here, you've got this common mode signal of 10 millivolts RMS because it's bouncing up and down the whole cartridge here at 10 millivolts. So this input and this input is moving at 10 millivolts. So that's your common mode signal. So it's if the signal at the instrumentation amplifier Vout due to the common mode signal should be no greater than the smallest detectable signal, calculate the required common mode rejection ratio. So we've done this in class before. We're talking about some RMS signals here, but the principles are exactly the same. And what we're saying is if the smallest signal from the cartridge is 400 nanovolts RMS, and we don't want a common mode signal greater than 400 nanovolts RMS, calculate out the common mode rejection ratio. So let's have a little look at this question. So part C. Smallest detectable signal equals 400 nanovolts RMS. Want common mode to be less than or equal 400 nanovolts RMS at output. And common mode signal equals 10 millivolts RMS. Therefore, the required common mode rejection ratio at INA output equals 10 millivolts, milli, not mega, over 400 nanovolts equals 25,000, which is the same as 87.96 decibels. And when you're answering the questions like this, it's good to give both numbers and give the ratio of the common mode signal to the common mode signal to the error signal, and also state it in decibels. Okay, and the decibels is 20 log of 25,000. Now, I'm conscious that we're just about finished part 1. So we will briefly look at part D of the question. So for calculating out this, the common mode rejection ratio, oops, we need to get some of that and some of that, some of that. This one here we've worked out is what was it, 25,000, which was 87.968 decibels. Part D is during the design phase, the cartridge must be capable of producing a peak amplitude on the vinyl record of 90 micrometers at 1000 hertz. What is the corresponding peak electrical output signal from the cartridge? Now, if you remember earlier, we had this strange equation here. And what I'm asking here is plug in some simple numbers here to this point here and work out what the electrical output signal. We know what 2 is, we know what pi is. I've told you the frequency here is 1000 hertz. And A is the amplitude of the recorded groove on the vinyl record, 90 micrometers. So all you need to do is plug 90 and 1000 into this equation here, and you land up with a maximum Vt, which is the velocity. And in this part of the equation here, I've told you that for a standard test, when Vt equals 5 centimeters per second, the cartridge outputs 5 millivolts per second. So all I want you here to do is calculate out Vt in velocity and then convert it into millivolts per second. What you do need to be a little careful of is think about peak and RMS. So just doing the maths for part D there, we know velocity equals 5 centimeters per second goes to 5 millivolts output. And these are both RMS values because we're reproducing 1000 hertz sine wave. And from question, V of t equals 2 times pi times f times a, which for a is the acceleration. So calculating from A for A equals 7.95 micrometers. Which equals 11.3 micrometers peak. So if you plug in these figures here, you land up with A equals 7.95. Our requirement is for 90 micrometers peak. Therefore, VT equals 56 centimeters per second peak, which equals 40 centimeters per second RMS. So and because we know output is linear, because of here and because of here, then for 90 micrometers will equal 40 millivolts RMS at 1000 hertz. So there we've worked out what part D is.